Well, welcome again to Math 315, Analysis and Topology. This is the second video for Chapter 1. And we finished off last time by proving this very important so-called arithmogeometric inequality, sometimes called the AMGM inequality, which simply said that if you take two positive numbers, then their average is always bigger or equal to the square root of their product. This is called the arithmetic mean, and this was the geometric mean. And we gave a little proof of that. And I wanted to mention now some generalizations of this. We begin with just the generalization to what happens when you've got three numbers. So if you take three numbers A, B, and C that are all positive real numbers, then again you take the average of the three, you add them up and divide by 3, and that is always bigger or equal to the cube root now of the product. So the square root in the earlier version now becomes a cube root, the cube root of A, B, C. This one is harder to prove, we're not going to do that here. And the whole thing generalizes completely, which I'll mention here and we might use occasionally, and that is if you've got n positive real numbers, then you take the average of these, you add them all up and divide by how many there are, and that's bigger or equal to, and now we have the nth root of their product. So you can see that if I take n to be 2, I get back to the original version. N equals 3 gives me the version up here, and this is the full general case. This is actually fairly difficult to prove. We're not going to do that here. Now in both of these generalizations we have equality, that is these are equal to each other, if and only if all of the numbers we start with are the same. So up here, if A and B and C are all equal, then we get an equal sign here, which is easy to see. And similarly here, if these are all equal, then we get an equal sign here. Now we're going to use this AMGM inequality to derive other inequalities. And there's a couple of these in the tutorial problems. I'll just do a couple of little simple examples here. The first one is if we take any number, any positive real number, and we take it at its reciprocal, then the answer we get is always at least 2. The answer we get is always at least 2. So here's a little proof of this result. So here we have it. We take x big positive, and I'm going to take x plus 1 over x. And so I'm going to look at the average of x and 1 over x. So I'm going to apply the arithmogeometric inequality. So the average of x and 1 over x, I add them and divide by 2, is bigger or equal to the square root of the product of these two. That's x times 1 on x. But of course x times 1 on x is just 1, and so I get a 1 here. And that means I can then multiply both sides by 2, which is positive, doesn't change the inequality. And so I have x plus 1 on x is bigger than 2. Which, if you think about it, sort of makes sense. If you take a number less than 1, positive number less than 1, and you take its reciprocal, the answer will be bigger than 1. And it turns out the sum of the two then is bigger or equal to 2. You get equality here if and only if these two numbers are the same, that is when x equals 1. So 1 plus 1 over 1 actually equals 2. Okay, second example, and these sorts of problems turn up in the higher school certificate in the 4-unit paper, extension 2 paper, so it's sort of gelling in here to high school maths at an advanced level. So here we take A, B and C positive, and we want to prove that if you add A plus B plus C, you take the sum of three positive numbers, then that's bigger or equal to the square root of the product of A and B, plus the square root of the product of A and C, plus the square root of the product of B and C. And so we're going to again use the AMGM inequality to prove this result. So here's our little proof of this, and all I'm going to do is I'm just going to use the ordinary simple AMGM inequality. I'm not going to use the generalized versions. So I start off with A, B and C positive, and all I'm going to do is I'm going to apply this AMGM inequality to each of these, to all pairs of numbers out of here. So I'll pick A and B firstly, So I simply write down the AMGM inequality for A and B. So the average of A and B is bigger or equal to their square root. And now I'll do the same for, and by the way, I can now move the 2 up to here. So I get A plus B is bigger than 2 root AB. Now I'm going to do the same thing for B and C. So B plus C will be bigger or equal to twice the square root of BC. And then I'll do the same for C and A. So C plus A is bigger or equal to twice the square root of AC. So I simply apply the same AMGM inequality 3 times. Now you keep your eye on the goalpost. We're trying to get A plus B plus C, so it looks a sensible thing to do to add each of these 3 inequalities. Everything is positive, so we can do that without any problems. I'd simply add together the 3 of them. So I'm going to get A plus B plus B plus C plus C plus A on the left side. And that, of course, is just 2A plus 2B plus 2C. And on the other side, I'm getting this plus this plus this. So I write that down. And now, of course, you look at that and say, well, I can divide everything through by 2. And so I do that, and there's the desired result. That's the result we were looking for. In the next little section, we're going to have a look at some basic limits. And before we come to look formally at the precise meaning, the precise definition of limits of sequences, I'm going to here briefly revise the basic idea of limits of functions heuristically. Now, by heuristically, I mean just by using our common sense without doing anything particularly fancy. So we will come back and formally define very precisely what we mean by a limit of both a sequence and a function, but here we're just going to revise our basic limits that you will have seen hopefully in earlier courses, and how to deal with these limits, both limits as we go off to infinity and limits at a point. So the first thing to remember is that you'll recall that as the values of x become larger and larger, then the value of 1 over x becomes smaller and smaller. So 1 over a super huge number is very small. I'll make this much more precise later, but here I'm just going to rely on our intuition. That is, if you take 1 over a very large number, the answer is very small. Formally, we're going to use this notation, which I'm sure you've seen. It's the limit as x goes to infinity. I like to read this as x becomes very large. Be very careful with infinity. Infinity is not a number. It is simply an idea. And you never ever see the symbol infinity with an equal sign. The equal sign and the infinity sign should never appear together. You can't say something equals infinity. This is simply a shorthand way of saying what's happening to 1 over x as x becomes very large, and the answer is that 1 over x gets very close to 0. And that's what we mean when we write this down. I'm not saying 1 over infinity is 0. That doesn't mean anything. I'm saying that as x becomes very large, 1 over a very large number gets closer and closer to 0. And in the limit, we say this limit is equal to 0. So I'm going to just begin with a nice, fairly simple example. I'm going to show a couple of examples of how to deal with these slightly more complicated limits, and we're going to begin with a nice simple one. We're going to look at the limit as x goes to infinity of x over x plus 1. That is, what happens to this quantity here as x becomes very, very large. So I've dealt with this here, and I want you to think about this in the following way. So I've got x on x plus 1. So if someone offered me $1 million or $1,001, which do I take? Do I take the $1 million or do I take the $1,001? And the answer is, I don't care. I'll have either. If someone offered me $1 million or $1,001, I won't argue with them. I'll take whichever of the two they care to give me. Because, of course, compared with $1 million, $1 is nothing. it doesn't really do much. It doesn't amount to much. It's the $1 million that captures my attention. Now that is a nice analogy which you should keep in mind with these limits. That is, you ask, where's the money? So when I look at this limit here, I've got a very large number here, x, which is becoming very large. And on the bottom, I've got that same very large number plus 1. Well, who cares about the 1? If I offer you $1 million or $1 million plus 1, it doesn't matter. They're roughly the same size if x is very large. And so when you divide them, you would expect to get the answer. This should get closer and closer to 1. The plus 1 here really doesn't do anything. I'm not cancelling it out. I'm simply saying that as x becomes very large, this quantity gets closer and closer to 1. Now there's a formal way of writing that out, and that is we're going to divide top and bottom by the highest power of x in the denominator, which is x. So I'm going to divide the top and the bottom by x. Whatever you do to the top, you can do the same thing to the bottom. So I divide by x. So x over x is 1, x over x is 1, and then 1 over x is just 1 over x. Now we use our intuition, because we know that 1 over x goes to 0 as x becomes very large. And that means as x becomes very large, this term here is disappearing, it's going to 0. And I'm just left with 1 over 1, which is 1. And that's how we're going to set it out when we're doing these problems. So let me do a slightly harder example here. And actually, before we do that, let me just summarize what we've just done there. So we're going to use the following basic rubric here, and that is when dealing with limits involving rational functions, that is polynomials over polynomials, or a bit later we'll see anything involving polynomials. The basic rule is divide by the highest power of x in the denominator. That's the important rule. Divide by the highest power of x in the denominator. So we're going to have a look at this limit here. We've got x becomes very large, x cubed plus 1 on 4x cubed plus 3x minus 2. So here's my working for this one. So I'll give this limit a name. I'll call it L. Just, it's always good things to give things names in mathematics. Then you can refer back to them. So there is our limit. I look at the limit, and the first thing I ask is, where's the money? If x is very large, what are the terms that become the biggest? If x is 1 million, where's the money? Well, that's going to be the big term on the top, because that's the x cubed, and that's going to be the big term on the bottom, 4x cubed. So that's where the money is. These are what we call the dominant terms. Now sure, 3 times 1 million is very big, but 4 times 1 million cubed is so much bigger. So although this number here is becoming big, this one is the dominant term. This is becoming big more quickly. So our basic, we firstly identify the dominant terms. And so heuristically, sort of making a guess, we would expect the answer to be 1 over 4, because these don't amount to anything. And we'll see that, of course, is the answer coming out. Now, for the setting out of this, we apply that rule. We divide by the highest power of x in the denominator, and that's x cubed. So I'm going to divide both sides, top and bottom, by x cubed. So x cubed over x cubed becomes 1. Then I get 1 over x cubed. 4x cubed divided by x cubed is 4. 3x on x cubed is 3 on x squared, and then minus 2 on x cubed. So we divide everything by the highest power of x in the denominator, and that's x cubed. Now we simply use our intuition here. We know that x becomes very big. 1 over a very big number is going to 0 in the limit. I'm not saying 1 over x cubed equals 0. I'm saying the limit of 1 on x cubed is 0. Okay, there's quite a difference in sense. This term here is going to 0 in the limit. This term here is going to 0 in the limit. This one survives, that one survives. I just get 1 over 4, and when you simplify, you get a quarter. And so there is the limit of that particular function there. Now it's always good, I think, to do a couple of examples. So I'm going to do another example on the same thing, and so this time I'm going to do the limit as x goes to infinity of 4x squared minus 2x plus 1 on 2x squared plus 3. So I'll just do a second example, very similar to the one we just did. And here it is here. And so 4x squared minus 2x plus 1 on 2x squared plus 3. And again, first thing you do is you say, where's the money? There it is there. There's the dominant term. That if x is very large, that's the term that matters. And on the bottom, that's the term that matters. So again, just common sense to predict what the answer should be. This is just noise. This doesn't amount to much compared with these terms. And so this is really just 4x squared on 2x squared, which of course cancels down to 2. And you can see that is the final answer. But in the setting out, we're going to divide each term by x squared, because that's the highest power of x in the denominator. I'll leave you to check the algebra here. I'm just dividing everything through by x squared, top and bottom. I get this expression here. And again, as x becomes very large, this is going to 0, this is going to 0, this is going to 0. I just get 4 over 2, which is 2. And that's the value of the limit. Now I want to do one more of these, because so far the limits we've had, they all existed. We could find what their value was. Here's a slightly different, it looks very similar, but slightly different example. Here we've got 4x cubed minus 2x plus 1 on 2x squared plus 3. So what's happening in this case? Well, in this case, we're going again to divide. We go to our limit. We ask, where's the money? There it is. That's where it is on the top, and that's where it is on the bottom. Now, our rule is always to divide by the highest power of x in the denominator. Not the numerator, but the denominator. So the highest power of x in the denominator is x squared. So I'm going to divide everything in sight by x squared. So this time I'm going to get a 4x minus 2 over x plus 1 on x squared, and on the bottom I get 2 plus 3 over x squared. Now if you look at these terms, as x becomes very big, this one's going to 0, this is going to 0, this is going to 0, this just stays at 2, but this term here, this 4x in the numerator, is becoming very large as x becomes very big. So that means as x becomes very big, we're getting a very large number on the top, and we've only got 2 on the bottom, and so the limit is just getting bigger and bigger. So the 4x term in the numerator becomes large as x becomes large, hence this limit, we say this limit does not exist, or we sometimes say that this limit, I've called it L, arrow infinity. Do not write L equals infinity, that is not mathematics. L is a real number. Well, whatever this thing is, you can't put equals infinity. Infinity is not a real number, so you can't use it with the equal sign. So I would write here L arrow infinity, which is a short way of saying L becomes as big as we like, as x becomes as big as we like. In this case, the limit does not exist. There's no finite value of this particular limit. Okay, well, there's more of these to look at in the tutorial problems. There's one final example I'll give here, slightly more difficult example, and this one here is we might, I think, save for the next recording.